Okay, so welcome to multivariable calculus. This is lecture 7. And so what we're going to do today is Taylor series. So some of you might have done Taylor series in Math 140 or in Calculus BC. It's not one of the prerequisites for this course. Eventually, we will do Taylor series for functions of several variables. We're going to start off with Taylor series for functions of one variable, and we're going to get some dividends for all the stuff we've been doing on sequences and series. We've been talking about how can you tell if a sequence or a series converges. This is one of the reasons why we care so much about this, is we want to try to replace complicated functions with simpler ones. Okay, so the idea is we're going to be looking at polynomials. Why are we going to look at polynomials? Anybody give me a reason why we might look at polynomials? 1x, x squared, x cubed. Why might we look at polynomials? Just making sure that everybody's able to get in. Hello? Okay, I will let you next time. Please try to get in by 9. Okay, so why might we look at polynomials? When you think of functions you can understand, do you think of exponentials? Do you think of logarithms? Do you think of cosines and trigs? Polynomials are simple functions. So let's start off with simple functions. Let's see what we can do with them. If you're willing to roll up your sleeves and look at more complicated functions, you might be able to do better. And so a lot of modern information theory actually uses more complicated functions than polynomials. And they have a lot better properties than simple Taylor series like this for many things. They can more efficiently transmit information. And so later in the semester, we'll actually have a lecture where we talk about how do you send streaming video? How do you use something like this to send information quickly? If you wanted to send this information, you could send it pixel by pixel, right? Very, very trivial math to do that. And then if you wanted to send a split second later, you could send it pixel by pixel. This is a tremendous amount of information. Now, our phones, our internet, our Wi-Fi is getting so much better that it's not as big of a deal now as it used to be. But there's a huge benefit for efficiency. And so instead of using polynomials, you could generalize this and just have a nice sequence of functions. We're starting off with 1x, x squared, x cubed. If you go to linear algebra, a huge part of linear algebra is about looking at different bases, different sets of objects to describe the space you want to look at. And so we're looking at what can be described as combinations of the simple functions 1x, x squared, x cubed. So if I give you a function, one possibility is I just give you a series expansion. And I just ask for what values of x does this converge? You should be able to give me at least one value of x where it converges. So can someone give me one value of x where this will converge no matter what I give you? Yes. 0. Yes, when in doubt, be a smart ass, choose 0. Almost surely that will work. Every term vanishes then but a naught. It's not clear if I give you a sequence of a's whether or not any other value of x will work. And in fact, if I take a naught to be, if I take a n to be n factorial, it turns out it will work for no x other than x equals 0. In general, however, you'll have some region of x, maybe x between -3 and 3, maybe x between -0.5 and 0.5, where things will converge. Or maybe x between -0.5 and 1. Maybe when x is negative, you're getting some alternation in sign that helps. And so for each series, you want to figure out what's the largest range of x that this converges for. Well, we don't have to expand things about x equals 0. We could expand things about another point, x equals c, and then just write the expansion in terms of the functions 1, x minus c squared, and so on and so on and so on. This has the advantage of letting you shift to where the action is. If the action is happening at C, let me expand about what's going on at C. If I'm trying to describe what's happening with my car and I want to model where will I be in a few seconds, and I know after 1 hour, I'm 48 miles from home, traveling at 62 miles per hour. That's below the speed limit, don't worry where I am. I don't really want to be expanding things about time equals 0. I want to be expanding things about time equals 1 hour because that's where my information is. I want to know what's going on around that period of time. Okay. So the first is a theorem about when a power series like this converges. And so it says that there is some number r, which is greater than or equal to 0. It could be infinity. If r is finite, then f of x converges absolutely when x minus c is less than r and diverges when x minus c is greater than r. If r equals infinity, then it converges for all x. So there's a way to determine for any power series this magic number r, and it will tell you if x minus c is less than r, it's going to converge absolutely. If it's greater than r, it's going to diverge. So the question, of course, is how do we calculate what r is? Well, we just spent several days doing different tests for when does a series converge or diverge. Can somebody give me some tests to figure out when a series converges or diverges? What's a test we could use? Ratio test. What else could we use? Root test. Root test is the best of them, but the ratio test is easier to use. Ratio is my go-to if divine inspiration doesn't work. But I can't just quickly look at this and see what the answer is. But you can use the ratio test and calculate rho. And if, depending on what rho is, it's going to converge or diverge. For different choices of x minus c, it might converge or diverge. So for example, let's let an equal 1 over 2 to the n, and let's let c equal 3. I'm choosing 3 because I can draw a 3 without having it look like a 2 or a 5 or an s or whatnot. It doesn't really matter. So let's calculate. So rho would be the limit as n goes to infinity of an plus 1 over an. Although here, let me change this a little bit. I'm going to call this bn. And here, bn is going to be an x minus c to the n, which would be 1 over 2 to the n x minus 3 to the n. How could I write that? I could write that if I wanted to as x minus 3 over 2 all to the nth power. And just do a little bit of algebra and put it all together. And so now if I want to calculate this limit, it's the limit as n goes to infinity of x minus 3 over 2 to the n plus 1 divided by x minus 3 over 2 to the n, take the absolute value. That's the limit as n goes to infinity of x minus 3 over 2. So that's going to be my rho. Okay? This is actually a pretty nice limit to calculate as n goes to infinity. What would be the limit as n goes to infinity of this? So as n gets larger and larger and larger, what does x minus 3 over 2 go to? Sorry? Why would it go to infinity? So when n equals 15, what is x minus 3 over 2? So when n equals 15, what would x minus 3 over 2 be? How'd you get 6? So when n equals 15, what do you get for x minus 3 over 2? What about when n equals 2013? So what's the limit? As n goes to infinity, what's the limit of x minus 3 over 2? Yeah, it's just x minus 3 over 2. This has no n dependence. Everything worked out really nicely. And so I'm taking the limit as n goes to infinity of something that has no n dependence. Oh, well, if it has no n dependence, it's always x minus 3 over 2. It is just x minus 3 over 2 in absolute value. So we want rho to be less than 1 to converge. So we need x minus 3 over 2 in absolute value to be less than 1. So x minus 3 is less than 2. So what is the range of x that would have x minus 3 less than 2 in absolute value? What does x go from? So I want x minus 3 to be less than 2 in absolute value.
Go between -2 and 2.
Okay, so if I take x to be -2, I would get -2 minus 3 is -5. It's 1 and 5. It'd be 1 less than x less than 5. Let's see why. So we want x minus 2 to be less than 3. So there's two possibilities. I could have x minus 2 is positive or x minus 2 is negative. So I could have x minus 2 is less than 3 or negative x minus 2 is less than 3. In the first one, I get x is less than 5. And in the second one, I get negative x plus 2 is less than 3. Negative x is less than 1. X is greater than -1. So if I look at the real line, here's 3. The first one, x less than 5, that's going to give me going like this. For the second one, I have x is greater than, did I make a mistake? Oh, I wrote x minus 2. I switched things. This is why the numbers aren't working. I switched the 2 and the 3. When you see me doing bad algebra, please speak up earlier. Okay. So let's do it with the right numbers. I wrote x minus 2 less than 3. It's x minus 3 is less than 2. So we have x minus 3 in absolute value is less than 2. So either x minus 3 is less than 2 or negative x minus 3 is less than 2. And so from the first one, I get x is less than 5 or negative x plus 3 is less than 2, negative x is less than -1, x is greater than 1. And not surprisingly, when you do the correct algebra, it works out. Okay. And so here we go. So here's 3. When x is 5, we see as long as x is less than 5, we're okay with the first one. So that gives me all of these values. And for the second one, we need x to be greater than 1. That gives me all of these values. And so the ones that will work are the ones right in between. So this is the slow way of just going through and seeing, what does this inequality mean? What does it mean for x minus 3 to be less than 2? If x starts to get really large, x minus 3 is going to clearly be greater than 2. If x is very negative, it's clearly going to be greater than 2. It's what's the sweet spot? Well, there should be one value of x where you can look at this and you know that this will be less than 2. What value of x can you look at and say, oh yeah, I know this is going to be less than 2? 3, right? Be the smartass, right? If I just take x equals 3, I make this 0. Okay, I know I'm okay there. Well, what's going on if I take x equals 3? That's taking x to be c. Oh, I'm just plugging in 0 for everything over there. It should clearly converge in that case. The question is, how far away can I go from the point of expansion? If I take x to be c, it's going to be fine. How far away can I go? And this tells me, using the ratio test, I can go all the way up to, but not including 1 and 5. Now, if I wanted this to be greater than 1, the ratio test would tell me it diverges. So if x is either equal to 1 or 5, we know it's going to diverge. The question is, what would happen if I took x to be 1 or 5? What we've done here won't answer that question. It doesn't answer what happens at the endpoints. That's okay. So there's a big result. We're not going to go into the proof. This is what you need more advanced analysis classes for, term by term differentiation. Basically, this says what you want to do, you can do. If I give you, 2 functions, The derivative of a sum is the sum of the derivatives. If I give you 3 functions, the derivative of a sum is the sum of the derivatives. What happens if I give you infinitely many functions? It's no longer necessarily true that the derivative of an infinite sum is the infinite sum of the derivatives. Every time you see an infinity in mathematics, you have to be careful. It requires you to do some work to justify whatever it is you want to do. And we'll see later some examples in multivariable calculus where I can't switch the orders of integration because an infinity is at work. But if I have a series that converges absolutely, that I can differentiate term by term in that region, I can integrate term by term in that region. And the radius of convergence of these new series is the same as the old. So you can differentiate term by term. That's wonderful. Okay, so this is a great result. If the series converges absolutely, you can differentiate term by term inside that region of convergence. Okay, so here is basically how we start to do a Taylor series. So T is for Taylor. So this is a degree n Taylor series. And again, you should always have a story in mind when you're doing this. So for me, I think of f as my distance. So your x is time, f is distance. So if x is time, f is distance, what would f prime represent? So velocity. What would f double prime represent? Acceleration. What would f triple prime represent?
Acceleration.
No, f double prime is acceleration. What's f triple prime? It is a jerk. So the triple prime is a jerk. I forget what the 4th derivative is. There's a lot of words that we don't really use. We don't really use what it's called for the 3rd derivative. There is a name for the line in a fraction a over b. It's one of those things we really almost never use. For most things, it's very fortunate that it's the 1st and the 2nd derivatives that really matter. But we can take more and more and more. If you think about what's going on, I have a finite polynomial. So when I have a finite polynomial, I can differentiate term by term without any trouble. Imagine I'm trying to approximate where I am as a function of time, and all I know is my initial location. If all you know is your initial location, f of a, what's your best guess for where am I a minute later? All you know is at time a, you're at f of a. I'm sorry? I have not given you any information about speed. All you know is that time a, you're at f of a. What's your best guess for where you are 1 minute later? I'm sorry? Nope. F of a. What's your best guess for where you were 3 seconds earlier? F of a. What's your best guess for where you are 2 hours later? F of a. If I give you no information other than where you are at time a, all you can say is, I'm going to guess that you're f of a for all eternity. So this is the 0th Taylor order polynomial. So the 0th order, t0 of x would just be f of a. Now imagine I give you your instantaneous speed at a. So now we can do the 1st order. So that would be t1 of x is f of a plus your instantaneous speed at a times the elapsed time. And if you think about what's going on, if this is my function and this is time a, I'm doing the tangent line approximation. And so this point over here would be a f of a. The slope is f prime of a, and the tangent line is y minus f of a is f prime of a x minus a, or just rewriting y equals f of a plus f prime of a x minus a. So the 1st order Taylor series is just the standard tangent line approximation. And note, t1 prime of x, so what would I get if I take the derivative of t1 of x? What's the derivative of f of a with respect to x? So what's the derivative of f of a with respect to x? What's the derivative of 17 with respect to x? This is a prerequisite for the course. What's the derivative of 17? 0. What's the derivative of 23,408? Doesn't matter. It's a constant. What's the derivative of f of a with respect to x? 0. It's just a constant. Now let's look at the f prime of a times x minus a. F prime of a is a constant. A is a constant. What's the derivative of f prime of a times x minus a? I'm taking the derivative of this with respect to x. What would that be? So if I just gave you x minus a, what's the derivative of x minus a with respect to x? 1. Now I multiply it by a number. What's the derivative of f prime of a times x minus a? It's just f prime of a. So we just get, this is just equal to 0 plus f prime of a times 1. So t1 prime of a equals f prime of a. So the first order Taylor series, it equals the function at a. So note t0 of a equals f of a. And its instantaneous speed at a agrees with the instantaneous speed of our function. So the first order Taylor series agrees with the function at a, and its first derivative agrees with the function of a. What about the second derivative of t1 of x? What would be the second derivative of t1 of x? It's just 0. So it's not necessarily going to agree anymore. So it's going to agree at the value of the function and the first derivative, but not necessarily the second derivative. What do you think might do a better job than the first order? No, the Rebel Alliance. Sorry, second order. Are they still called the Rebel Alliance? I wasn't sure if they were called that or if they were now the Republic. All right, second order. So we would have t2 of x is f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a squared. Now, what would the second derivative, what would the first derivative of t2 prime of x be? Well, f of a, we've already done that. F prime of a x minus a, we've already done that. So this is going to just be 0 plus f prime of a x minus a plus f double prime of a over 2 factorial times 2 x minus a. And let's calculate the second derivative. So you'd get 0. Oh, sorry, there's no x minus a up here. Sorry, this is just 1. So when I take the derivative of f prime of a times 1, what do I get? So what's the derivative of f prime of a times 1? I think I heard someone say it. It's just 0. And now I have f double prime of a over 2 factorial. I take the derivative, I have 2. The derivative of x minus a is just 1. I'm going to actually write this as 2x minus a to the first power. So it becomes 2 times 1 times x minus a. I'm sorry, I no longer have the x minus a. Just to make it a little bit clearer what's going on. And now note t2 of a is f of a. t2 prime of a is f prime of a. And t2 double prime of a is going to be, let's see, f double prime of a over 2 factorial times 2 factorial. That's just f double prime of a. And you can keep going. And if you wanted to do the nth order Taylor series, you would see that the first n derivatives agree at a. So for the nth order, t of a equals f of a dot dot dot. The nth derivative, and we put the n in parentheses to say the nth derivative at a is the nth derivative at A. So what we're doing here when we look at the Taylor series is we're trying to come up with a good approximation to our function. And we're choosing a polynomial of degree n. Which polynomial? There's a lot of polynomials we could do. We're trying to make things match up as well as we can at the key point A. And then the hope is that if they match up well at A, they'll match up well nearby. Okay, so just a little bit more formally, if your function is infinitely differentiable, then we would say that the Taylor series at some point C, I'm sure there's a reason why they went from A to C, is exactly what we did before, except rather than stopping at n, you just go off to infinity. As soon as you see an infinite sum, you have to be afraid. So what's the first question you have? When you see this, what's your questions? So you see this infinite sum, what do you want to ask? So I've given you an infinite sum. What's the first question you should ask when you're given an infinite sum? Does it converge? So one, does it converge? And if so, for what x? The next is, what does it converge to? Does it converge to, what would you like it to converge to? I'm sorry? Yeah. You want it to converge to 0. So we have some function f. We construct the series by looking at what's going on at this point C. And we might be lucky enough that this sum converges. What would you like this infinite sum to converge to? I'm sorry? Well, this is going to be different for different values of x. And if I give you a, I'm sorry? Well, f of c is just 1 point, so then that would be saying you'd want this to be constant. We have something that's changing for different values of x potentially. We start off with a function f. We calculate its value at c, its derivative at c, its second derivative at c, its third derivative at c. We keep calculating all of these derivatives, and we bundle them together, and we make this new infinite function. What would you like this function to converge to? Do you want it to converge to cosine of 13x minus sine of exponential of x? Yes. I'm sorry? Okay, so what would you like it to converge to? Well, t of x is that infinite sum. What would you like t of x to converge to? What function? F of x, right? We're trying to build a function from f. It's the only function other than t that's on the board. We want it to converge to f of x. Right? The whole idea is to take a complicated function and replace it with simpler functions and understand how we build them together. And the hope is that this will converge. So what do you think the answer is to 1? Do you think it's always going to converge? Do you think we'll always converge? So not always converging. And sadly and amazingly, can converge to something other than f. That is horrible. I should not be able to write down an infinite sum that converges based on the information on f, and it converges to something other than f. This tells you that the subject is difficult. And that's why we have advanced math classes to talk about when will it converge and converge to the function you care about. Okay, so There are various theorems that you can prove about how much of an error do you have when you approximate your function. And so this is a really nice one. It says if I take the nth order Taylor series and I take some point x and I look at the value of my function and I subtract off the value of the approximation, then it's less than or equal to some constant k times x minus a to the n plus 1 over n plus 1 factorial. N plus 1 factorial, what happens to that as n gets larger and larger and larger? What happens to n plus 1 factorial? It grows really rapidly. If you have a calculator, you might be able to get somewhere between 60 and 86 factorial on your calculator. If you start going beyond that, your calculator says no thank you. And so it's going to give you an overflow error. But what about the x minus a? If n is fixed, maybe n is 50. That's going to be a huge number down there, but it's still a fixed finite number. If x equals a, what's the difference between x minus a? What's the difference between x and a if x actually equals a? 0. So if I take x very, very close to a, 1 over a quadrillion, then I'm going to raise that to a huge power, and that's going to be really small. So even though the denominator is growing if n is large, if n is fixed, it's just some number. I just take x really close to a, and that will make the top as small as I want. Well, what about this value k? It turns out that this value k is related to the largest value of f prime, of the n plus first derivative. So if we assume the function has n plus 1 derivatives, and we assume that the n plus first derivative is bounded, we can actually bound the difference between these. So if you want, I've included a link to a proof that I wrote up years ago using the mean value theorem and the intermediate value theorem and going through the proofs of these as to how you would get this bound. Well, not exactly. I was lazy. I did not want to get the best possible bound. So I had said something, but nobody really caught me on it. I talked about how n plus 1 factorial is getting really, really large. Is that a good thing or a bad thing for us? What do you think? I seem to be implying it was bad, and we can balance it by looking at the top. Yeah. Yeah, it's a large denominator, right? You should be saying, wait, Professor Miller, we've got an n plus 1 factorial here. Isn't that helping us? Yeah, the larger n is actually, the better the error bound is going to be because we have this huge factor. Now, there is some, I would say, suboptimal notation here. And so I am a huge fan of notation that just has indices like subscripts and whatnot up the wazoo, so that when you look at it, you know what's going on. Which is k sub f n plus 1. So k depends on the function f, in particular depends on its n plus first derivative. So if you want, you could even say, or it depends on the n plus first derivative. You could also put in something about maybe the interval that you're expanding it about. But when you just write the letter k, it looks like it's just a constant. Well, as I change n, I change the value of k. Because this is the largest bound. This is a bound for the largest value that the n plus first derivative can take on in my interval. And so it's quite possible that as I take higher and higher n, k could be getting larger and larger and larger. And if k is getting larger, what does that do to the error bound? So if k is getting larger, what does that do to the bound that we have for the error? Is it helping us or hurting us? So how is it helping if k gets larger? How does that help us with the error bound? So I tell you, the error is at most 50 or the error is at most 100. Which is better for us? 50. So as k gets larger, what is this doing to us? It's hurting us. Now, as k gets larger, if it's getting larger because n is getting larger, we're also getting some extra decay down here, which might be able to help us. And if x is really close to a, we're not taking it to a higher power, and that can help us. So you have a lot of different competing influences going on when you're trying to see what's the best bound I can get. The n down here helps us. If x is close to a and this is small, the n up here helps us. But maybe k is growing with n, so it's not clear what's the best choice to take. So if you go over here, if you're interested, I go through and talk about how you can prove bounds like this. I don't prove the best possible bounds. I wanted something very simple. And so the bounds I prove basically drop the n+1 factorial down below. It's not the best we can do, but for a lot of things, it's often enough just to have some bound and get a sense of what's happening with x. The main thing is for fixed value of n, you get a sense of what is the error like in terms of x minus a. Okay. So the next one is one of the standard theorems that if you have some interval c minus r to c plus r, assume f is infinitely differentiable, assume that there's a series of derivatives of f that are always less than or equal to some fixed number k, then the Taylor series converges and converges to the function. So this is a very special situation. We have to be looking at an interval where all of the derivatives are bounded by one number. So note, k is independent of n. So in that special case when there's no dependence on n, if you go back to what you had in the previous page, well, since k is independent of n, as I just take more and more terms, this is going to get smaller and smaller and smaller because of the growth down here. And that's why it's going to converge. Okay. So one of the things I want you to learn is how to live in the 21st century. So I like to use Mathematica primarily because when I was young, that's what I used. And you all know, first mover effects, whatever you use first, you for the most part get stuck with it until they no longer support it, which is why we're in this situation of my migrating web pages because SFTP is no longer being supported after numerous decades. This is some very simple code in Mathematica to calculate Taylor series. And so we are going to have probably some classes remote where I will have you watch some videos and just play with Mathematica to learn how to do simple things. Mathematica can differentiate, Mathematica can integrate, Mathematica can plot. Because it can do all these things, you should learn how to get it to do it for you. If you don't want to download Mathematica to your computer, you can use it often in some of the libraries. There's also Wolfram Alpha online where you can just do simple command lines. If you want to just integrate one function, you can do that. You can't write beautiful programs like this. Who here has programmed? Okay, I have violated one of the cardinal sins of programming in this very short code snippet. What did I not do that I should have done? Define variables, put in comments, make it possible for somebody other than myself to read what's going on. So when you get old, you get lazy. If you're writing a short 3-line, 4-line program, it's not a big deal. When you're writing something that's 10,000 lines and you may not be the one using it, well, maybe it's advantageous for you for only you to understand your code. But it's nice to put in some comments so other people can read what's going on. So what I'm doing here is I'm basically defining coefficients. I'm using some if statements. This means if when you divide n by 4, you get 0, I want cosine of x naught. If when you divide it by 4, you get 1, I want negative sine of x naught. If when you divide by 4, you get 2, I want you get negative cosine of x naught, and otherwise sine of x naught. And then what I'm going to do is this is going to be the nth order approximation to the cosine function about the point x naught, and I'm just defining it as a series expansion. And then I'm going to manipulate as a wonderful command. I'm not going to do that today. I'll say that for later. It allows you to visually change things and zoom in on different points and whatnot. In the interest of just having things work, I'm just manually putting in, where is it? Okay, some specific choices right here. So here I am plotting cosine from a little bit beyond -2 to a little bit beyond 2. And I'm looking at the 0th order Taylor series approximation at the point 0. And I get a straight line. Now, if I take cosine of x, what's the derivative of cosine of x? I'm sorry? Derivative of cosine of x. Negative sine of x. What is negative sine of x at 0? 0. So if I try to find the first order Taylor series expansion, I can actually use the same picture, because if f of x equals cosine of x, f of 0 is going to just be 1. F prime of x is negative sine of x. F prime of 0 is going to be 0. So the first order and the second order Taylor series are the same. The next one, however, will be interesting. The second order Taylor series will be fundamentally different. So what's the derivative of sine of x? Cosine. So I get negative cosine of x. And so f double prime of 0 is going to be negative 1. And what you can see is that this is where those statements I had before came through. What's the derivative of negative cosine? I'm sorry? Positive sine. And so then we would get the next one, f triple prime would be sine of x. And what would the fourth derivative be? So notice it cycles. So I'm going to just keep getting the same string again and again and again of coefficients. 1, 0, negative 1, 0, 1, and just on and on and on and on. And so if I look at the second order Taylor series expansion, this is my best fit parabola in some sense to the cosine function near x equals 0. Does this do a good job? I would say so. Does it do a good job for all values of x? So no. Is there any way that this could do a good job for all values of x? Well, what do you know about a parabola? What's going to happen to a parabola as x goes to plus or minus infinity? It's got to go off to infinity. And what do we know about values of cosine? Where does cosine live? What are the possible values of cosine of x? Yeah, negative 1 and 1. So we know there's no way that the parabola can work for all values of x, but it does a pretty good job between -1 and 1. That's a pretty good region where cosine of x, so the second order Taylor series expansion, is just going to be 1 minus x squared over 2 factorial when you do the calculation. If we did the third order Taylor series expansion, it would be the same thing. So if we go up to the fourth order Taylor series, so here's the third order. You can see over here, the image is slightly a little bit bad, but that's actually the number 3. We're doing a third order Taylor series. If I look at the fourth order Taylor series, it's doing a pretty good job now, almost all the way up to -2, 2. What do you think would do better than a fourth order? Not fifth. Because the fifth is going to be the same as the fourth. So instead of the fifth, you should go up to the sixth. And so if we look at the sixth, now we're basically getting it almost from -pi to pi. Okay, if we go even further, this is now the 12th order Taylor series expansion. And so if we do the 12th order Taylor series expansion, this is a very good fit, well beyond -pi. When I'm evaluating cosine, do I need to have an input outside of -pi? No, because we could always assume that our input is between -pi and pi. Now, again, this is because cosine is periodic. Every time you increase by 2 pi, you return to where you were. You could, of course, try to come up with a series expansion that works for all values of x. This works for -pi to pi extremely well. And so here is the 30th Taylor series expansion. And at this point, you can't really tell the difference between -10 and 10. And we can keep taking more and more terms. So I've plotted now the difference between the 15th order, I'm sorry, the 30th order Taylor series expansion and our function. When you look at this, it's so close to 0, it's tough to see. As I start getting around -3, oh, okay, it's a little bit noticeable relative to that, but it's still extremely small. It's less than 0.01 in absolute value. Whenever you have things that are this close in this region here, it's tough to see. It's better to plot the difference. And so here's a plot of the difference of the function and the Taylor series approximation. Do you think it's really that ragged and nice? This is Mathematica having some rounding errors in doing the calculations. They're of size 10 to the negative 16. It's basically saying for the level of precision you've set, I really can't tell the difference between this and 0. It's really, really good. So here is one of my favorite functions. So this is the function e to the negative 1 over x squared if x is not 0, and 0 if x equals 0. So here's the plot of the function. If you think about e to the negative 1 over x squared, if x is 1 over 100, then you get e to the negative 1 over 100 squared. Okay, 1 over 100 squared becomes 10,000. So this is e to the negative 10,000. Is e to the negative 10,000 big or small? E to the negative 10,000. So e to the negative 10,000 would be 1 over e to the 10,000. That's really small. If I replace, instead of doing 1 over 100, if I did 1 over 1,000, I'd get e to the negative 1 million. Really small. This function is decaying extremely rapidly near 0. As a nice exercise, you can go back to the definition of the derivative and you can calculate what is the derivative of this function at 0. You have to use L'Hopital and you would get that the answer is 0. So I'll make this extra credit. And then you have to calculate the second derivative and you use L'Hopital and you get 0. And then you use L'Hopital again to calculate the third derivative. What do you think you get? 0. And if you calculate the fourth derivative, what do you think you get? 0. All of the derivatives of this function are 0 at 0. Let's think about what that means. At time 0, I'm at 0. My speed is 0. My acceleration is 0. My jerk is 0. All of my changes are 0. And yet I somehow move. So if we were to calculate the Taylor series of this function, the Taylor series actually converges for all values of x to the function that's identically 0. This is why math is such a hard subject. I should not have a Taylor series that converges for all x and only agrees with my function at x equals 0, where it has to, because I write my function as f of 0 plus x, or x is 0, plus x squared, that's 0. Here is a zoom in to give you a sense of just how small it is. Looking at the value, you can't see any difference between this and 0. Okay. So I'm going to just end with some nice exercises. You should go through and calculate what's the Taylor series of sine, what's the Taylor series of cosine, what's the Taylor series of e to the x. And a big question is, of course, how do we define e to the x? Do we define e to the x as this Taylor series? Do we define it as, you might have seen this through compound interest? And then can somebody tell me either what I squared is or I squared am? So I is the square root of -1. What's I squared? -1. So it turns out e to the ix is cosine x plus I sine x. This is one of the most useful identities in all of mathematics. You can prove all of your trig identities in less than 5 minutes once you know this. You need to know this, and you need to know e to the ix, e to the iy is e to the ix plus y. And so later in the semester, I'll show you how to prove double angle, angle addition, half angle formulas. All of this follows immediately from this. All right. And then just, I'm going to skip the binomial stuff for now. And I'll just end with, here is the homework that's due next time. So just a couple of problems on power series, a couple of problems on Taylor polynomials. And then we will pick up Taylor series again later in the semester once we start looking at functions of several variables. This completes, the first chapter, chapter 10. We're going to skip chapter 11, which is on, I think, parametric stuff and whatnot, and go straight into vectors. So I will send an email later today. I can go home and deal with a sick kid right now.